let us see some applications of the convergence theorems that we have studied. Let's begin with a simple application of the monotone convergence theorem. Consider the function f of x equal to x bar s, where x is greater than 0 and 0 if x equal to 0. Look at this function. Now, if s is greater than or equal to 0, we know that f is in fact bounded on close 0 1 and is Riemann integrable there, and what is the Riemann integral of this function going to be? Well, it's just going to be x bar s plus 1 by s plus 1 limits 0 to 1 which is just 1 by s plus 1. Right? Now what about s less than 0? Okay, well then in this scenario the function x bar s blows up near 0. So the function cannot possibly be Riemann integrable. But is it Lebesgue integrable at least? Well, we can see that. How do we see that? Define the sequence of functions fn of x by x bar s if x is greater than or equal to 1 by n and 0 if x is less than 1 by n. What we are essentially doing is, since the function blows up near 0, we are truncating the function at the point 1 by n and setting it to be 0 when it's closer, when x is closer to 0 than 1 by n. Okay, so essentially what we have done is we have sort of cut the function off before it blows up. Clearly fn converges to f pointwise. Right? Furthermore, what is integral of fn 0 to 1? Well, it's just integral 1 by n to 1 of fn, which is just going to be it's going to give us x bar s plus 1 by s plus 1 with the limits 1 by n to 1. If you substitute this, you will get 1 by s plus 1 into 1 minus 1 by n power s plus 1. Okay, now observe that if s plus 1 is greater than 0, then 1 by n power s plus 1 converges to 0. Okay, which means that the sequence of integrals fn is bounded. Furthermore, fn is obviously an increasing sequence. Therefore, by the monotone convergence theorem, f, the limit of that, which is just 1 by not 1 by the limit function f given by x bar s is also Lebesgue integrable, and its integral is limit n going to infinity 1 by s plus 1 into 1 minus 1 by n power s plus 1, which is just 1 by s plus 1. So the functions x bar s are all Lebesgue integrable provided s is greater than -1 and its integral is what you would expect, 1 by s plus 1. Excellent. So this was one simple application of the monotone convergence theorem. Now let's see another application. Recall that if we have a uniformly bounded sequence of continuous functions, it need not have a subsequence that converges uniformly. We have studied this extensively when we studied Ascoli-Arzela to find out when you will have subsequences that are uniformly convergent. In that context, we had studied this example sin nx, which is uniformly bounded. This is a uniformly bounded sequence of continuous functions. And we had actually shown by an ad hoc argument that no subsequence of sin nx can converge pointwise to a continuous function, to a function. Forget continuity. You cannot even have a pointwise convergent subsequence of sin nx. Forget about uniformly convergent subsequence of sin nx. And we had constructed an ad hoc clever argument. Well, now we can give a more conceptual proof. Suppose for some subsequence we have sin nkx converges to some function f, let's say. Okay, now this just means that limit n going to infinity of sin nk plus 1x minus sin nkx whole squared, this goes to 0, right? But what is inside is dominated in absolute value by 4, right? That's the maximum possible value that you can get for sin nk plus 1x minus sin nkx, which means this means that integral over I, or not I should mention what I is, integral over 0 to 2 pi of sin nk plus 1x minus sin nkx, the whole squared, this limit must be 0 as k. One second, I made a slight error. This is k going to infinity. Okay, here also it's as k goes to infinity. Okay, so what was I saying? Yeah, since we have this is dominated by 4, this means that sin nk plus 1x minus sin nkx the whole squared limit must be 0 by dominated convergence theorem. Here we are using the fact that the function 4 is Lebesgue integrable on the interval 0 to 2 pi. It is obviously because it's Riemann integrable there. But you can check by calculation that this is not 0. This is not 0. I think it's pi or 2 pi or something like that. Just evaluate this expression and do the integration and find out the value. You will notice that this limit is not going to be 0. It's going to be pi or 2 pi or something like that. So here is a scenario where we have shown that sine nkx cannot possibly converge pointwise to a function f. That's not possible. It will violate it will violate the dominated convergence theorem. Okay, yet another application is how to show of course, let me mention a trivial application. Interchange of integral and summation. So I'm not even going to elaborate this any further. So let me just verbally say what I mean by this. Suppose if you have a sequence of Lebesgue integrable functions, non-negative, and you look at their sums, and let's say their sums converge to a function, then you can evaluate the integral of the sum as the sum of the integrals, provided that the sums are all dominated by a single Lebesgue integrable function. So I leave it to you to formulate a version of the Lebesgue's dominated convergence theorem for series. It's not too hard and it's very useful also. Okay. Finally, another application is how to determine whether a function is Lebesgue integrable. So what happens is, often we do not have the full force of Lebesgue's dominated convergence theorem. We do not have mod fn's all dominated by G. We might have somewhat restrictive hypotheses. Let me just state that as a theorem. Let fn be Lebesgue integrable and fn converge to f almost everywhere pointwise. Suppose G greater than 0 is in L of phi and mod f is less than or equal to G almost everywhere, then f is Lebesgue integrable. Notice the crucial difference between this theorem and Lebesgue's dominated convergence theorem. In Lebesgue's dominated convergence theorem, we had that each fn is dominated in its absolute value by G. Here, only for the limit function we have that property, yet the function f will be Lebesgue integrable. This is very useful to show that certain functions are Lebesgue integrable. Let's see how to prove this. Proof. Now, what can happen? It can happen that fn of x is greater than or equal to or g of x or in fact strictly greater than g of x, or fn of x is less than minus g of x. Okay, both of these can happen. At those points where fn is less than g of x or fn is greater than minus g of x, then we have that mod fn of x is less than or equal to g of x at those points. But there could be many such problematic points where either fn is greater than g or fn is less than minus g. So what we are going to do is modify fn to get rid of bad points. Well, how do we do that? Well, at those points where fn is greater than g, we are just going to truncate it to g. At those points where fn is also less than minus g, we are going to set the function to be minus g. Well, there is a fancy formula you can write down that does the job for us. You define gn of x to be the first you take the minimum of fn and g. what this would do is, if it so happens that fn exceeds g, then it will just truncate it to g at that point. Wherever fn is less than g, this will continue, the function gn will continue to be fn. Now this does not take care of those points where fn is less than minus g. So to take care of that, what you do is you put a minus g here and take max. So let's think what happens. Let's take the three possibilities. Suppose it happens that fnx is less than or equal to g of x, and minus g of x is less than or equal to this. That is, we are in the good point. X is a good point where everything is maintained. Well, what will happen is, when you take minimum of fn comma g, you will end up with fn. And when you take maximum of fn comma minus g, you will end up with fn again. So this complicated looking function does nothing if x is a good point. Now if fnx happens to be greater than g of x, then this minimum of fn comma g will be just g. Then when you take maximum of g and minus g, because g is a non-negative function, you will end up with g. So at a bad point where fn exceeds g, you still end up with g. Similarly, if fn is less than minus g, then what will happen is, minimum of fn comma g would actually end up with g again. And when you take maximum of g comma minus g, so sorry about that, let me clarify again. If fn is less than minus g, then minimum of fn comma g would actually be fn, right? Because fn is in fact less than minus g, therefore it's less than g. Now when you take maximum of fn comma minus g, because we have fn is less than minus g, you will get minus g. So at those points where fn dips below minus g, you will get minus g. Okay, so the net upshot of all this is mod gn is less than or equal to g almost everywhere. And also we have gn is Lebesgue integrable, because it's a maximum and minimum of Lebesgue integrable functions. And it's also easy to see that since fn converges to f almost everywhere, gn converges to f almost everywhere. Okay, net upshot is by dominated convergence theorem, f is Lebesgue integrable. Okay, this is another useful thing to remember about showing how to show a function is Lebesgue integrable. This is a course on real analysis, and you have just watched the video on applications of the convergence theorems.